Let's get started on the last session of the infrastructure modernization track. I hope everybody's had an interesting and a useful day thus far. As the title suggests, this is all about GKE, networking with GKE. GKE is Google Kubernetes Engine, our managed Kubernetes offering. So in the next 35 minutes or so, I'm going to be talking about how to think about architecting from a networking standpoint when it comes to rolling out GKE for your application workloads. Now, GKE is an extremely popular service in Google Cloud. And what we've seen in terms of various interactions with our customers is invariably something like this. People start out with a small cluster, and then they grow big. They start deploying more and more, right? But along with this, the one challenge that customers tend to face, and I apologize for this complex slide, but the one challenge that people tend to face is what we call as route SCOTA. What is a route SCOTA? What this basically means, actually, route SCOTA refers back to one of the fundamental assumptions that Kubernetes makes, which is every pod in a cluster should be able to talk to any other pod in that cluster, whether it's on the same node or if it's even on another node. And for that to happen, for a node, let's say, or for a pod in one node, which needs to talk to a pod in another node, that will really need to use some of that route SCOTA that we provide through our VPC. So as your clusters grow, the route SCOTA tends to get consumed and fully exhausted. So that used to be a challenge where people would approach us and say, I've run out of my route SCOTA. Can you please help me give more routes so I can go on increasing my cluster size? With that context in mind, we used to have only one option, which was this routes-based cluster that you could build in GKE. For some time, though, we've now had this option called as VPC native clusters. It is enabled by default, so there's literally nothing that you need to do, but it's a strong recommendation that anytime you deploy a new GKE cluster, you consider doing it through VPC native clusters. What that lets you do is actually bypass the whole routes cluster, the route quota requirement. It reduces the need for that, but it also enables and activates new features, because as the name suggests, VPC native, it means that the cluster is now integrated much more closely with the VPC. And that then enables new things like shared VPC, GCLB integration, anti-spoofing checks, etc. So all these new capabilities also get enabled for your GKE cluster anytime you use it using VPC native cluster. So literally, that is the first best practice, which is ensure that you always use VPC native option when you deploy a new GKE cluster. Second, and this is more about IP address management. For any of you who may have deployed a Kubernetes cluster, you will realize that Kubernetes tends to use IP addressing fairly liberally. And if it does use that IP addressing fairly liberally, it means that you will invariably start running into some of these problems if you've not thought through some of these things beforehand. Things like, oh, I've only got so much contiguous IPs, and then I have another bunch of CIDR, which is a whole different block, right? And my network administrator has only given me this particular block, which then I need to fit into my entire cluster. How do I mitigate this? There's a couple of things to think about. When you enable VPC native cluster, which we just spoke of shortly, it also then activates three types of IP address CIDRs that you can then use within your cluster. One is what we call as the node CIDR, which is literally nothing but the same subnet range that you will typically use for any VM that you deploy in a VPC, so nothing different. But the other two are secondary IP ranges. One is for all the pods that you run in your cluster, and the other is for services that you run on top of those pods. So you can allocate secondary IP address ranges to both services and pods. And that means that if you allocate discrete ranges to those, you can now very well control the size of those CIDR ranges, and also apply policies on top of those. The routes, the firewall rules. You can put in a firewall rule which says, my on-premises folks in subnet X should only be able to access pods running with IP address range A.B.C.D. Right? So you can put in such sort of firewall rules. How do we do that? There's two ways to do this management of IP address ranges. You can let Google manage it for you, which in many times will work out okay, and which is the option we call as the auto option that you see up on left. So we will manage the pod range, we will manage the services range, we will also manage the node range itself. Or in some cases, especially if your cluster size is small, but you may have a need to hold a lot more pods, cram more pods, that's when you may want to use the custom option, which is something that you see up on the other side, which obviously, as the name suggests, gives you the control to decide what sort of CIDRs you're going to give to the pod, to the CIDR, and to the nodes. Another knob that you can tweak and which may be helpful is deciding on the number of pods that you expect on an average, or on a max basis, sorry, on a per node basis. So as you can see up here, I can allocate a big pod range, let's say a /24, to all my pods across the cluster. And then I can go and allocate a smaller sized pool out of that, say a /24 for the entire cluster that you see up on top, but then /28s, discrete /28s, or say /27 for the other node pool, so that I can be very, very efficient in how I use my pod IP address range. Right? So you expect to maybe just run 10 pods, let's say, on a per node basis, then you can put that number in, and GKE will automatically optimize your pod IP address range and let you optimize for having more nodes in your cluster. Or you can do a reverse of that approach, or you can say, you know what, I don't expect to build a lot of nodes in my cluster, but I do expect to have many pods in my node. So this is the sort of trade-off and the options that you can play around with when it comes to IP address management for GKE. And this is how it all comes together. So again, not going to go through all of this, but the point here is once you've decided what are the nodes that you need in your cluster, you accordingly allocate a CIDR for that. In this case, it's, let's say, I need 12 nodes for my cluster. Great, let's allocate a /28. It gives me 16 IPs. I need to run 20 services in every cluster. Fantastic. Let me use a /27, which will give me 32 IP addresses for all my services, so on and so forth. So that's the idea of planning your IP address allocation for services, pods, and nodes well ahead, so you do not run into issues around, oh, I've suddenly run out of IP addresses. Kubernetes tends to use a lot of IP addresses. Great. So let's switch gears and talk a little bit about security, because this tends to be a hot button topic in almost all our conversations. So when we think about security for GKE, specifically for the GKE clusters, there's a couple of things that come up. Number one, customers tend to say, Google, I want to deploy my GKE cluster with absolutely no ability for that cluster to access anything on the internet. It should be totally hidden from the internet. Or second, I want to be able to access all these Google services that you provide privately without having to go over the internet. Keep in mind all our managed services like BigQuery, Bigtable, Spanner, etc., GCS, all of these by default are accessed through a public API, which you access over the public internet. But some customers, especially enterprise customers, heavily regulated customers, will actually turn around and say, we want to be able to access these from the cluster without ever having to go to the internet. Or things like, how about private connectivity to my API server, to my cluster master? And if I want to be able to reach to any third-party API, they want me to whitelist the particular IP I'm going to be coming from. Right? So let's talk about those options. Really, it boils down to these three things, or these three steps, that one needs to activate when it comes to securing your GKE cluster from a connectivity standpoint. Choosing the cluster type. There's two types of clusters that you can build, public cluster or a private cluster. Expose the cluster master, which means that the master node, which is actually the brains of the control plane of your GKE cluster, do you need to expose that privately or publicly? And third is, if you're going to be exposing the cluster master, where or which sort of IP addresses do you want that particular master to be accessible from? So first thing, private clusters. As the name suggests, anytime you select a GKE cluster to be a private cluster, it does a couple of things. One, it means it will never have any public IP addresses, external IP addresses, allocated to any of the nodes in your cluster. What does that mean? If it doesn't have a non-RFC 1918 IP address, it means it can never go out on the internet. If it has to go out on the internet, you have to necessarily use a cloud NAT for outbound internet access, which means you control what servers can go out on the internet and without ever having to expose them directly. So that's point one. Point two around private clusters is also the fact that they let you access, we automatically enable the ability for you to access all those Google services that I previously mentioned. So that's a default option that many customers, or an option that many customers tend to use, enterprise customers tend to use, which is make my GKE clusters totally private. So as we saw, you can access this from on-premises while using private IP addresses. There is no default outbound access. It's blocked. The only way to access outbound is through a NAT. And third, at the bottom, you see that if you want your cluster to be able to access any of the Google services, then that becomes available too by default. The second aspect of this is, what about the master itself? What if I want to access the master either privately or publicly? Let's say I'm coming on premises through an interconnect or through a VPN, and I want to be able to access the master that is running for my cluster. I can either enable a private endpoint, which again, as the name suggests, all private connectivity, there's no public internet access, or in some cases, I can also enable a public endpoint if the use case so demands it. So you've got a road warrior, an application developer who can access this public cluster from a particular IP address anytime he wants to, or you can also put in a blacklist which says, only trust this particular set of IP address ranges, let's say for the blue set IP address ranges. Anything else, don't trust them, which means no access. And that's what we call as a master authorized networks. So again, not going to go through all these details, but the point again is you can enable various sorts of connectivity. This describes this in some more detail. You can enable various sorts of connectivity for your master node, for your actual GKE nodes, in terms of using a public cluster option or a private cluster option. Cool. Moving on to another aspect that we see many times with the large GKE deployments, which is the aspect of DNS optimization. DNS, as I'm sure you're aware, is a key component of any Kubernetes deployment. It is used for intra-cluster name resolution. One of the things that we've heard from some customers is, Google, you tend to size the kube DNS service, which is actually a couple of pods. You tend to size them on the basis of the number of nodes that I allocate to my cluster and the CPU cores that you allocate to the cluster. What if I don't have a huge cluster, but I still want large DNS, I still expect large DNS consumption because I happen to use Node.js or some other service which tends to use a lot of DNS. What can we do then? What we can do then is to use this service or this capability called as DNS Autoscaler. Using DNS Autoscaler, we can go ahead and tweak the config map, which lets us actually, I don't know if you're able to see this here, but there's one component in that red line that you see, which refers to min. So I can actually put in a command in there which says, irrespective of the number of nodes that I may have or the number of CPU cores that I may have, I absolutely want a minimum of 5 DNS replicas to be running in my cluster. Right? So I'm no longer bound by the logic of how many CPU cores you have, how many nodes you have. I know I expect to use a lot of DNS. I'm going to be putting in more DNS replicas for myself. Yet another element around DNS optimization is the fact that some applications tend to use DNS a lot. Again, Node.js comes to mind. But then you can actually optimize their DNS resolution process by using things like avoid search path expansion. And there's two ways to do it. Either you use your application to actually do it, which is, anytime you do a DNS name resolution, use a fully qualified domain name and end it with a dot, with a DNS period. That means it's not going to waste time trying to look for other alternatives. Either do it at your app level, or alternatively, do it in the pod config, DNS config, where essentially you achieve the same thing. Great. So these were some fairly basic infrastructure best practices: security, IP address management, DNS. Let me now step up a bit and talk about services, Kubernetes services. How do you run them at scale, and what are some of the things to be mindful of? So from a resiliency standpoint, one of the questions we get asked is, how do you make sure that I can continue to run my services without any disruption, even if I'm making changes to my application? How do we make sure that my end user doesn't see any of that and his app experience is uninterrupted? For that, one needs to be able to appreciate the life cycle that a pod has. And when we think of a pod life cycle, there's really three kinds of checks which come into play. One is what we call as the liveness check, liveness probe, which literally means, is the pod alive or not? And if it's dead, then that's it, game over, it's dead. But on a serious note, if it's dead, liveness probes helps to ensure that if a pod is not alive, then to restart it and make sure it's alive. So that's kind of the first check that comes into the life cycle. The second check is what we call as the readiness check. And this is used when you're doing a large deployment, which automatically means multiple pods to be deployed for different types of services. How do you make sure one particular pod has actually booted up properly before your deployment goes and spins up another pod? So that's kind of the second lifecycle check. And the third one is more of a load balancer-based check, a health check, which is typical of any load balancer. And it's all about, how do I make sure that not just the pod, but also the network infrastructure path is actually alive, so that I can ping that on a particular port, and I know that it is alive and healthy, and I can send traffic to that port. So keeping these three in mind, this is how they start to pan out. So anytime a pod comes up, liveness check is done. Once the liveness check is passed, that's when you see that particular check is turned green. Then comes the readiness check. Readiness check is trying to make sure that not only the pod is alive, but it's actually booted up gracefully. And finally, the health check, which is the load balancer actually now trying to check, is the pod able to receive traffic from a network path standpoint as well. But on the flip side, and you can see down below, if you see at the green graph down below, serving traffic, as the health check has passed and pod goes into the pod ready state, you see the traffic picking up. But on the flip side, the moment Kubernetes, which is the container orchestration system and which decides which container lives and which dies, the moment Kubernetes decides a particular container has to be terminated, it will then send a SIG-term signal to that particular pod, which is basically a signal to that pod saying, you will be terminated soon, so whatever it is that you're doing, start finishing that work up. And there's a couple of things which happen as soon as a pod receives a SIG-term. It will start draining any work that it is doing, and it will also, if you go back, you will see that it will also start failing the readiness and the health check right after the SIG-term comes through, right? Which means it will start draining whatever it is already doing, and it will stop accepting anything new. And in fact, because it's failed the health check from a load balancer standpoint, the load balancer is no longer going to send it traffic. So by default, after 30 seconds will come, after SIG-term is sent, 30 seconds after that, you will get the SIG kill, which means now the pod is going to get terminated. And if you expect your application to behave differently, make sure you tweak that timer. Also, in some instances, you may have a dependency on an external appliance or a third-party appliance, right? You may have another load balancer sitting outside, and you may want that to be ready before your pod can accept traffic. So you can also put in readiness gates of your own on top of the existing lifecycle, which is to say, unless this particular third-party appliance is ready, don't start sending me traffic. Cool. Another best practice to consider is how we do load balancing for Kubernetes. But before I get there, let's define the problem statement. By default, let's take this example. You've got a load balancer at the top. You've got two pods, pod A and pod B. Traffic's coming through. Everything's working fine. You decide to scale your application, right? You decide to now consider adding more pods to your application. So instead of just A and B, you say, OK, let me add a couple more pods, C and D as well. Great. What happens now? So traffic hits the load balancer, but then something odd happens. You notice that even after adding these new pods, most of your traffic is still ending up at those old pods. It's not actually going, it's not equally being equally distributed across all the new pods that you've set up. Why is that happening? Why is that happening? And the fundamental reason behind that is the default way in which the load balancer is working is that it is load balancing on the basis of the nodes, the VMs in which those pods are running, and not load balancing directly on the basis of the pods themselves. It doesn't have visibility of the pods, right? So when the traffic hits the VMs, there is another kube proxy component that runs inside all GKE nodes. The kube proxy actually does a load balancing a second time to be able to decide where to send that traffic to. And if you're running things like, even if you add those new backends, traffic is actually getting balanced to the VMs. So this is the default behavior. And if you're happening to use some newer protocols like HTTP2, Quick, etc., chances are you will be reusing those existing connections. So that behavior will be even more lopsided in favor of the existing pods. So traffic will continue to go, 80% maybe of your traffic will continue to hit the existing pods. Only a small portion will go to the new pods. So then you will say, that doesn't sound very smart. Why do I want to be in that position, and how do we fix this? Well, there's two ways to fix it. One is go ahead and reset those connections ever so often. Again, that doesn't sound very smart. That goes against how the newer protocols are designed, HTTP2, etc., which tend to reuse the existing connection that you've already built rather than opening new and new TCP connections. So you obviously don't want to use that as long as possible. The other option that we made available for a while now is what we call as container native load balancing. As the name suggests, now you're load balancing directly to the pods and not just to the VMs that are holding those pods. And because you're load balancing directly, let me just show you in the diagram. Now that you're load balancing directly on the basis of the pods themselves, traffic will be far more better load balanced. Not just that, it comes with some other benefits too. Now there's no double hops in terms of load balancing, because first load balancing happens at the load balancer, then it happens at kube proxy. None of that business anymore. Second, great for visibility and debugging if you're troubleshooting, because your load balancer has an accurate view of the traffic that it is sending to the pods themselves. It doesn't have a view of just the node. It has a view of the pods themselves, which is what you care about. And accurate health checks, because your pods are themselves sending their health information to the load balancer rather than relying on the VMs. So best practice, wherever possible, consider using container native load balancing rather than using the default load balancing. All right, switching gears now to talk more about handling failures or building resiliency for your application infrastructure in GKE. One thing to think about is to build what we call as failure domains. And failure domains in this example is a couple of things. One could be, how do I protect myself against a node failing within my cluster, right? And the way to do that is to use this particular attribute in your YAML, in your deployment manifest, called as pod anti-affinity. What this basically means is, if I'm running, let's say, 2 pods for a particular application of mine, so that they can both handle traffic together, if I use pod anti-affinity with that particular application, it will ensure that both those pods never happen to be on the same node at the same time. Because if that node goes down, both my pods go down. So it will automatically ensure that 2 pods for that same service will always be scheduled on different nodes, which protects you from a nodal failure. So that's a data plane protection. From a control plane standpoint, in fact, even from another data plane protection, is to spread your nodes and to spread your GKE cluster across zones, which means even if a zone were to become unavailable within GCP, your nodes will still keep on functioning in another zone. Control plane, let me just step back. Control plane protection is through a feature called as regional cluster protection. Things like, what if my master, my control, the brains of my cluster go down? So use regional clusters. Regional clusters will ensure that not just your nodes themselves, but even the brains, the master, will be spread across 2 or 3 zones across the entire region. Lastly, a quick point around config plane protection. And it's a very basic thing. I'm sure everybody here is aware of it, but just to reiterate that point, which is never to deploy any new changes directly to your production environment. Keep a copy in staging. Make sure you do all your changes there. Test your changes. Once you've done those changes, they've gone through successfully, you're happy with them, you're comfortable with them, only then go ahead and deploy them in production. A quick and efficient way of doing that is to use things like label selectors. For example, if you create a label selector, app.whatever, deploy that first to your staging environment in your canary. Once you're happy with the testing, use that same config then to go ahead and deploy in your production. That means no fat finger errors, no config management risks or errors. So really, kind of wrapping this down, I know I spoke about a lot of things, and you may be wondering, where do I go tweak this? So I wanted to show you, take a couple of screenshots and show you all the features that I spoke about. I mentioned building regional clusters as a best practice. So you see when you're building the Kubernetes cluster in the console, in the UI, you have that option to choose the location type. So regional is selected in there. Second, use a VPC native cluster, which we spoke right at the beginning of our session. And as you can see, it is checked by default. And there's no reason in this day and age to not use it. So absolutely recommend you consider building VPC native clusters. Another one that you see at the bottom is the number of pods that you expect to be scheduled on a per node basis. Give this a reasonable value. This will help you in IP address optimizations. A couple other points that we discussed. Load balancing. Enable that HTTP load balancing. This helps you do container native load balancing. Private cluster, which we spoke of, which automatically ensures that none of your nodes will get any public IP. And if they don't get public IPs, they're not able to talk to the internet. So if security is a concern, that's the way to harden your communications that the cluster can have with the internet. And if you do that, you should also think about enabling master authorized networks, which is essentially a way of saying, I only want IP addresses from this range to be able to access my master node. That means nobody else can access it. Or you can say, nobody should be able to access my master range. Only I should be able to access it from within my nodes themselves. So wrapping it up, what are some of the best practices? IP address management is extremely important when it comes to Kubernetes deployments. Think about how you're going to deploy your cluster IP space. Ensure you use VPC native clusters. For security, optimal security, use private clusters, use master authorized networks. Pod lifecycle, we spoke about that. How do you make sure that any changes to your application or any service disruptions do not impact your user experience? So make sure you understand the pod lifecycle and you take advantage of the health checks that it provides. And the feature that we saw in the end, which is container native load balancing. Don't just rely on the default load balancing, which load balances only till the VM level. Make sure that you use container native load balancing, which load balances right down to the pods themselves. And lastly, understand what are the failure domains, what is the failure possibilities within your cluster. Protect and build resiliency at a data plane level. do so at a control plane level, and do so also at a config plane level. And that brings me to the end of my session. Hope this was useful, and hope you had a good day today here. Thank you.